Yep. All right, we're going to solve a differential equation here. This is your first homework question. So let's get after it. So we notice that we have a first order differential equation. It's a differential equation because there's an equal sign, which makes it an equation, and a derivative in it, which makes it a differential equation. First order being that the highest derivative it contains is the first derivative. This is called an initial value problem because there is a differential equation associated with an initial condition. That condition will be used to solve for the constant that we get when we integrate. All right, so the only technique that you have to know to solve differential equations in Calculus AB is separation of variables. It's very easy technique. It's the easiest of all of them. All right, so how do we do it? Well, we see there's a dy over here, right? And since it's upstairs, that dictates to us that everything's got to come to the left side, everything that has a y in it. So you have a times y minus 2 here. So that's great when things are written as products. You can divide both sides of this equation by y minus 2. And if you did that, you'd get that. All right, we're not going to go bananas and show all the work and crossing stuff out. There's no need to do that. All right, so now what about this stuff? Well, now here's your dx, right? That's in the basement. That's no bueno, right? You need your d whatever term to be upstairs. So you're going to multiply now this side by dx, so it cancels, and that side by dx, and so you end up getting this. And so now you essentially have separated the variables. You got your y's on your left, you got your x's on the right, but more importantly than that, the dy and the dx term are connected with multiplication, right? So in other words, if I rewrote this left side as 1 over y minus 2 times dy, and then this is obviously x minus 2 times dx. So that needs to happen. If this would have been like plus dx or minus dy, no good. It's not in a Riemann integrable form, but it is for us, so we're good to go. So we have the green light, so we're going to integrate the left side, and we're going to integrate the right side. All right, so left side, how do you integrate that? Back in the day, you might do a u substitution, and you're going to let u equal the denominator, u equal y minus 2. And then you notice that y minus 2 is a linear term, so it's a linear u. So these are the ones that you can do in your head. Do you know a function whose derivative is 1 over stuff? And the answer is yes, you do. It's ln, absolute value of stuff, times 1 over the derivative of stuff. So the derivative of stuff here would be 1. So 1 over that would be 1 over 1. Right? And you're like, oh, why do you have to do that? It's not a big deal. Well, now it's not. But if this would have been 2y, then it would have been a big deal. You'd have to multiply by half. And that is because when you go to take the derivative of this and you use the chain rule, right, you would go back to this term right here. If you don't believe me, try it, see what happens. All right, over here, integral of a sum is a sum of integrals. Integral of a difference in the integrals. So here we go. So integrate this. You get 1/2 x squared minus 2x. If you stopped here on the AP test, you would get hammered because what did you forget? That's right, the constant of integration. And technically, you should be adding it to the left and the right, right? Because you're doing an indefinite integral here and an indefinite integral there. But at the end of the day, you're going to subtract one constant over and bring it to the other side. So you really only have to show it on one side. And since we're looking to solve for y, I'm going to add the constant away from the y term. So this is what we get. And this would be an implicit general solution because we have not solved for y. So we have options here now. We can figure out the constant now by plugging this point in. You're like, well, what is this point? If y of 4 equals 5, that means the point 4, 5 is going to be on this guy. That's the x, that's the y. So plug them appropriately in and solve for c. And you can do that, and there's nothing wrong with that. For whatever reason this time, I'm going to go about it a little bit differently. I'm going to go ahead and I'm going to solve for y now, all right, which is different than how I solved this beforehand when I did it on paper first. Yes, sometimes I work the problems out first before I show you. All right, so here we go. So let's exponentiate both sides. So we're going to e to that side, and we're going to e to that entire side. You can't e each thing individually. So e to the ln, right? Those are inverse operations there. That's just going to be absolute value of y minus 2. They cancel, so to speak. And then you get this, which is, we got to do a little magic with this. So we end up getting this. It's e to all of that. And you might be like, all right, what do I do with that? You do have this e to c thing. And if you remember what we were talking about, you can rewrite this using a property of exponents that you learned probably in 7th grade. And I'm going to rewrite this as e to the 1/2 x squared minus 2x times e to the c. Okay? And you're like, how can I do that? Well, think about it. If you multiply these two terms, right, which they both have the same base of e, you would add the exponents. So you would get this. So you're just using that rule in reverse. Technically, I could have wrote e to the half x squared times e to the negative 2x times e to the c, but I'm not really interested in breaking this up. I wanted to get that c out of there. And the whole point of this now is at the end of the day, e to the c is just a constant, right? It's just a number. So I'm going to put that multiplier out in front here and get k, I'm going to change it now, times e to the 1/2 x squared minus 2x, right? And now this is kind of cool, but because I did this, because I've rewritten this as a constant times a function, I can lose the absolute value bars here because depending on the point that I pick will depend on whether or not k can be positive or negative, right? So since I can control k being positive or negative, then I don't need the bars, all right? So that's kind of like a little weird thing to do, but we can do it. So now to solve for y, I'm just going to add 2 over. So I'm going to get k e to the 1/2 x squared minus 2x and then plus 2, okay? This would be my explicit general solution. It's explicit because I'm solving y explicitly in terms of x. It's general because there's a constant in there. All right. We were asked to solve an initial value problem, and that initial value problem had the initial value of y of 4 equals 5, right? So remember, y of 4 equals 5. So this is my x value. This is my y value. So I'm going to go ahead now and throw that in. So 5 goes in for y, k e to the 1/2 x squared. So 1/2 4 squared minus 2 times 4. So let's see what happens here. So 4 squared is 16, right? Divided by 2 is 8. So that's 8 minus 8. So that works out fantabulously. All right, so e to the 0 is just 1. So howdy doody time, k equals 5. And now let's go ahead and just chuck it back in. So y equals 5e to the 1/2 x squared minus 2x and then plus 2. We'll give this one a blue happy cloud, okay? This guy is not your general solution, but because we solve for the constant, this is your particular solution, okay? Whereas this guy over here was your general solution to the differential equation. So this is a family of functions differing by a constant that are going to satisfy that initial differential equation, right? This is a specific function that satisfies not only this differential equation, but also this initial value. So in other words, the 0.45 would be on the graph of this right here. All right? Not so bad. Rocking and rolling. All right, let's go to the next question. All right, so the next question was dy dx equals y squared. And then we say where f of 1 equals 1. So this is an initial value problem because we have a differential equation, which happens to be in terms of y here. That happens sometimes. And we have an initial value of f of 1 equals 1, which, long story short, that means 1 comma 1 is on the graph of what we're talking about here, right? And that one there is that one there. Okay. All right, so let's go get them. So we got to separate the variables here. So again, the dy is up top over here, so that tells you everyone's got to come to that side. And so how do I get this over? I divide both sides by y squared. So if I divide this side by y squared, I would get 1 here. It doesn't just go away, right? I get 1. If I divide that side by y squared, I get that over y squared. All right, the dx is in the basement, no bueno. You got to multiply this side by dx, multiply this side by dx. Remember, there was a 1 there, so you'd get 1 dx. You don't have to write 1 dx, but you can write 1 dx if it makes you feel better. And so this is what we got. And so again, you might think, all right, variables are separated, integrate both sides. And you might be a banana and do something like this. And if I can insert that emoji right there, no good. That's not what this is, right? Not what this is, okay? It's only ln when what? Liam? That's right, when it's 1 over y. This is 1 over y squared. So that's not ln. That's going to be power rule. In fact, you might even want to rewrite this as y to the negative 2 times dy equals 1 times dx. So again, your y's and your x's are separated. The dy and the dx are connected with multiplication. I can't stress that enough. Sometimes when you do crazy, algebra and you're working things out, moving things over left and right, all of a sudden you're left with like y to the negative 2 plus dy. That means you got to start over because that ain't going to work. So we're good here. So we can integrate both the left and the right. Power rule, add 1 to the new power and then multiply by 1 over that new power. So that's what you get there. And then here, integral of 1, function of derivative of 1 is x. All right. What would happen here if I did this on the AP test? Dylan? Yes, you're correct. You would be in a lot of trouble. You get crushed for points. So what do you got to do? You got to add that constant of integration. I'll add it to the x side since I'm solving for y. All right, so what am I going to do here? Maybe I multiply both sides by a negative to take care of this part. And then at the same time, actually, you know what? I won't go too much here, all right? I'll just multiply both sides by a negative. So I get that. If I wanted to be a banana, I could write plus k, but I'll leave it as minus c. So now y to the negative 1, guys, is 1 over y. We all know this. So now if I'm solving for y, you can cross multiply and do that nonsense, but you can also be like, hey, I'm just going to flip you, and then I'm going to flip you. And that's a valid move, all right, with equality. So we're good to go there. So now what is that? All right, you got an answer there. Is that the particular solution? The question is, and the answer is no, because there's a constant in it. This would be your explicit general solution. So I got to get the particular solution. So the point was 1, 1. So I'm going to use that point to solve for c. So 1 goes in for y, and 1 goes in for c. Okay, what do you do here? Here you can cross multiply if you want. Multiply both sides by negative 1 minus c, however you want to think about it. Maybe I'll cross multiply to appease all the cross multipliers. So you're going to get this equals this. Maybe add the c over, right? So c is over here. Subtract the 1 over. Negative 2 is equal to my constant. Y equals, and then I'll go 1 over negative x. And then be careful now, right? So c is negative 2. So it's negative x minus c. So it's negative x minus c, right? So be careful. So if I get this, I'm going to get 1 over negative x plus 2. And if you want to be cool, you can write this as 1 over 2 minus x. And we'll maybe put green. Is this green? Oh, yeah. We're going to put a green happy cloud around this. This is your particular solution. All right. So in other words, this is a function that not only satisfies the original differential equation, but it also satisfies, whoa, mama, I don't know how I did that. Yikes. There we go. All right. It also satisfies that initial value. Okay. So that's kind of important. Whereas the general solution, yes, that's annoying me. Whereas the general solution right here is a family of functions differing by a constant that satisfies the initial differential equation. All right, so now here's the cool part that I asked you about. And I didn't really give you a whole heck of a lot of guidance on this, all right? I asked you to find the domain of this function. So back in the day when you would do domain of rational expressions like this, which is just a polynomial divided by a polynomial, you would be like, all right, well, the numerator is defined for all real values of x. The denominator is defined for all real values of x. So you would think that the domain would be all real values of x except any value that made the bottom 0. So you might even say that the domain of this guy would be for all real values of x, but x cannot equal 2. And that would be correct if this wasn't embedded in a differential equation problem. So I did give you a little note, if you remember, and the note said the domain of a particular solution to a differential equation is the largest open interval containing the initial value on which the solution satisfies the differential equation. All right, so this is the wrong answer because of what I just read. And you're like, how does that make any sense? Well, let's pull up Desmos. And I graphed this guy here, right? So I went ahead and I graphed our particular solution. And then I also plotted the point 1, 1. And notice where 1, 1 is on. There are two branches here. 1, 1 is on the branch where x is less than 2. All right. That is my dog Elvis, who is a banana. So if I go ahead and graph this now, just do x less than 2, just so that you see that it's green. This here would be the domain of your particular solution. All right. And that's because the initial value it contains on the open interval, negative infinity to negative 2. So long story short, and it's not the greatest explanation right there, you can't jump over spots where a function is undefined or where a derivative is undefined. All right. And it has to do with the fact that the derivative is a limit, which is a two-sided idea. I don't really want to get too much into it other than you just can't jump. So if you have a function that has branches separated by asymptotes, you got to figure out where your point is, put it on that branch. Oh, it's on this branch, and then state that interval. And that's basically it. It doesn't come up too much on the AP test, but it has come up, I think, a handful of times. All right, that is it. Get after it.